All right, folks. Welcome. Happy Tuesday. I really don't have any kind of announcements to make. It's going to be notes today, notes Thursday, and then you're going to have to make some time on Friday to take care of the quiz. Okay. So this week we're focusing on this would be section 8.3 of your book, and they introduced the number E, and they introduced the first kind of application involving E, which is compounding interest in bank accounts. So we'll do that, and really after this today, you should be able to do the entire homework assignment. We'll just do more variety on Thursday. So definition. The number E is a transcendental, big word, transcendental number known to have a value approximately equal to the following expression as x approaches infinity. So I'll just give you a second to write that. Here's the expression. Okay, just give you a second to copy that. Okay. So transcendental number is, there's not many numbers like that. The only other transcendental number you've studied in math is pi. And pi, even though you know it's around 3.14, when you first studied pi, you should have discovered it, which is that it's the ratio of circumference over diameter in any circle. And this, much like pi, it's an irrational number. It has no pattern to it in terms of its decimal places, and it has no end. So we're going to kind of go through the first few here, or I'll say a few, so you can see where this number is going. Why don't you make, let's see, seven rows. Make the first column a short column. And we're going to do 0, 1, 2, 10, 100, 1,000, and we'll do 100,000. So I'm going to do the work here on the side. Now, you don't have to write this step down if you don't want to, but really what's happening is I'm doing 1 plus 1 over some number to that number. So if I do, the first one will be where x is 0. And that is no bueno, because you have 1 divided by 0 that's undefined. So you can't even do the first one. Can't even do it. You could start now at 1, and here you'll start getting some values. So I'm just going to erase these zeros. And I'm going to make them 1s. So I've got 1 plus, that's 1, is 2. And so 2 to the first is 2. Now, when I write it in the table, I'm going to write it with 3 decimal places to the right. So that would be 2.000. And this is just so we can compare later on what's happening. All right, I'm going to erase that. Now I'm going to do 2. So I've got 1 plus a half. That's 1.5 for the second power. That's 2.25. I'm going to write it with an extra decimal place here. So 2.250. Do the next one. And this is, if you don't have a scientific or a graphing calculator, you really need one. You're going to need one from now until the end of the course. So make sure you get your hands on one. Now we're putting in 10. So that's going to be 1 plus 1/10 is 1.1. And then I have to raise that to the 10th power. So I got to do that in the calculator. Can't do that by hand. I'll be here for, a week. That comes out to be 2.594. So when people look at this situation, this table, the numbers are going up, right? They're clearly going up. But they don't go up forever. They do, there's a limitation here. And what I want you to do is, I want you to do the next 3 on your own. Okay? So grab your calculator and do for 100, and then do for 1,000, and then do for 100,000. And I'll set the timer for 2 minutes. Go ahead. Okay. So if you did 100, you should have got something like 2.705. 1,000 should have given you 2.717. And then 100,000 should have given you around 2.718. So it's hardly even changing now. And it's not going to change any further in terms of these first three decimal places. If you did a million or 10 million, you'd still get 2.718, and then the change would be visible, further down the line. So that's E's approximate value, 2.718. I'll write it over here. Okay. So just like pi is around 3.14, E is around 2.71. Right. I do expect that you use the E button in the calculator. Right? And that is going to, if you're not doing that, that is going to cost you points when we have this like on a test. If you're not sure where the E button is in your calculator, come to conference period and I will be happy to help you find that. So the first thing that we need to do with this is see how it applies to what we did last week. And that was graphing exponential functions. So I'm just going to write here, consider the function f of x equals e to the x power. Yes, of course. If you need to step away from your computer for a second, yeah, just let me know what's happening in the chat. That's cool. No problem. Now this is this would be a parent function, f of x equals e to the x. So I'm going to just make a chart here, much like we did last week. And I'm just going to use -2 to +2. And this is where you have to use the calculator. Because you're going to have to evaluate e to the -2 power. And I already have this written out, so we don't have to spend time doing it. You have about 0.13. Comes out to be 0.13. This one comes out to be about 0.37. And then I've got 0, 1. Right? E to the 0 is 1. E to the first, we said before, that's like 2.71 or 2.72 if you want to round it up, no big deal. And then E squared is about 7.39. And so I'm going to graph these. I'm going to go make a graph, go up to about 8. And we're still looking for the same information when we do the graphs. You're going to have to do domain, range, and asymptote. And your asymptote corresponds to your vertical change, right? And there is no vertical change with this. It's just a parent function. So it stays just like all the others last week. The standard asymptote is y equals 0. And then I'll plot my points. -2.1 is like just a hair above the axis there. -1.37, a little bit higher. 0, 1. 1, 2.71. And then 2, 7.39. See about there. And that's That's our curve. Connect the dots. See, it jumps up pretty quickly, pretty steep. And then as we go to the left, it flattens out, approaches the asymptote. So it's like it's an exponential function, just like any other. So its domain is all reals. And then if I look at the graph, the entire function is above a height of 0. So y is greater than 0. So in terms of the numbers in the chart, there's an E button in your calculator. So on a graphing calculator, it's above the division key. It's a second function. So you have to just go in and do e to the -2, gives you that. E to the -1 gives you that. E to the 0 gives you that. So you just have to go in. I calculated them beforehand for us. So, we didn't spend time doing that. But these numbers, like these are the numbers. Like if you're doing any kind of a graph involving base of E, this is the chart. Like this is the parent function chart. So you're going to need this to do any other kind of graph involving E. And we'll do one in a minute. Here. We'll do a little graph translation just to show you it's no different than what we did last week. So I'm actually going to leave this chart up here because you're going to use it. And remember, if you want where we wrote f of x equals e to the x, you could just write under there what that meant, right? Was e is like 2.71 about, right? So that's why we got the picture we got. It's when the base is above 1, it's growth, right? Which is why it rose as we went to the right. Exponential growth. So let's do graph translation theorem problem. So I want you to sketch and provide the domain range and asymptotes, all that business. Let's do f of x equals 2 times e to the let's say 2 times e to the x plus 3 and then minus 4. Okay, that's the function. 2e to the x plus 3 minus 4. And so, when we did this last week, it's the 3 steps, right? It's the parent function, which would be y equals e to the x, which I already have up here. And then you look for, what are the actions involved, right? The 2 different kinds of actions. Apply those actions to the table, and then come up with your table that you're going to graph. So since I already have this parent function table on the board, I'll just give you, I think 3 minutes is enough. Okay. Go ahead and try that. Three minutes. All right. So your actions, you're looking for your lateral movement, left, right, is tied to the exponent. The +3 is telling you you're going left. 3, graph translation theorem. That means I'm going to subtract 3 from every number in the x column. The other values involved in the function, you have the coefficient of 2, that's your compression. So you're going to compress a factor of 2, and then -4 would be down 4. Okay. And numerically, that means I'm going to have to multiply by 2, then subtract 4. Okay. And that's going to give me my new table. So I've got, let's see, if I subtract 3 from all these, it's going to be -5, -4, and so on. The other column, you're probably going to have to use calculator to do. So you've got the 2 times 0.13, and then subtract 4 from that. That's -3.74. You could just go with -3.7. You know, you're not going to know the difference at that kind of level of graphing. And you've got the 0.37. Multiply that times 2, subtract 4, -3.26. You can make it -3.3, I suppose. And then 1 times 2 is 2. Subtract 4, that's -2. And then 2.71, that's around 5.4. Subtract 4, it's about +1.4. And then 7.39 times 2, subtract 4, that's about 10.8. Now, what you're going to see as we go kind of further through this chapter is sometimes, last week we did some where the numbers were so big that I told you could omit a point. In fact, there's going to be other problems where you could actually omit 2 points because the numbers are going to be very large. It might not fit on the graph. And that's the reason why I've had you do 5 points all along, is if you have to leave 2 off the graph, you're still going to get an okay picture. So I'm going to graph all these. This is not that high up to go. So I'm going to make a graph that goes up to 11. No big deal. If you chose to omit the 10.8, that's, you know, that's fine. Remember, we're doing domain, range, and asymptote. And I've been telling you to put the asymptote on first. Asymptote corresponds with the vertical change. In this problem, that is down 4. So my asymptote is moved down 4. So it's right in here. That's the line y equals -4. And now I'm going to plot the rest of the points. So I've got -5, -3.7. It's like right on the asymptote almost. Then -3.3. It's like right next to it. -3, -2, you can start to see the jump. -2, 1.4. And then -1, 10.8 is all the way up here. All right, and so you can see the bend. Well, okay, and there's the picture. Domain, of course, is all reals. And the range, the function, the height of the function is above -4. So y is greater than -4. I'll just give you a few moments to copy any of that. But really, it's no different than what you did last week. It's just this parent function table is what's new. Okay. Now your book likes to throw in, for some reason, some questions about classifying as growth or decay. And I'm not sure you would know what to do with these, so we're just going to tackle a couple. I'm just going to put here classify as growth or decay. And we'll just do 3 problems real quick. These are not very long to do. So first one, f of x is equal to, let's do 1/2 times e to the 4x. 1/2 times e to the 4x. And this is the first problem in this chapter that I've shown you where the coefficient of x is not 1. If you remember back to the first day, when we defined an exponential function, it was a times b to the x power. Right? And there's no number in front of x. It's not b to the 2x or b to the 5x, it's b to the 1x. So what you have to do is you have to force the problem into this mold. And you're going to use properties of exponents to do it. You're going to use the power of a power property in reverse. You see, e to the 4x is the same as writing e to the 4th and then raising that to the x, because you're multiplying exponents. 4 times x is 4x. I haven't changed anything about the problem in terms of its value, but I'm rewriting it in a way such that if I go now into the calculator and I do e to the 4th, it's about 54.6. And that's how it has to look before you can answer the question. Because you need just the base raised to the 1x. So 54.6, that's a number that's greater than 1, so that's growth. Right? If it's a number that's greater than 1, it's growth. If it's a number between 0 and 1, it's decay. Let's do f of x equals 8e to the negative 3x. 8e to the negative 3x. So it starts the same way. You take the x out of the expression, right? And now e to the negative 3. I mean, you could write it as what it is, which is the reciprocal, but eventually you're going to have to go into the calculator and figure out, well, what is that? You know, what does that have a value of? And so e to the negative 3. Well, it's about 0.049 or 0.05. Okay. And that number is between 0 and 1. So that's decay. I'll just give you one to try real quick. Let's do f of x equals 1/3 e to the negative x. I'll just give you a minute. I'm not going to set the timer. So e to the negative x is technically e to the negative 1x. I guess that's a little bit of a curveball, I suppose. Right, so it's e to the negative 1. That's 1 over e, or, in the calculator, that comes out to be, we did that before, I think it was 0.37. And so that's also another decay. Okay, so you'll see a section in the homework that asks you to do these, and that's how you deal with them. Just give you a moment to write any of that down, and then we'll get to our last topic, which is the compound interest here. All right, here we go. So if you're at kind of at the bottom of your notebook paper, you might want to flip to the next page. This is going to take up a little bit of room. I want you to write in the middle of the page compound interest, and then we're going to break it into two categories. You've got compounding n times per year, okay, a certain amount of times per year. So when you open an account with the bank, they'll tell you, oh, well, we compound it, annually or quarterly, things like that. I guess we can write up here the common ones in case you're not familiar. For n, okay? So 1 time per year would be annually. 2 times per year would be semi-annually. I'm not going to write them all. 4 times per year would be quarterly. 12 times per year would be monthly. 52 weekly. 365 would be daily. They do use 365, not 365 and a quarter, right? From science, it's technically every year is 365 and a quarter. The banks don't give that quarter of a day ever. Doesn't matter if it's leap year or not leap year. It's always 365, right, for daily. If you have the other situation, that's called compounding continuously. So that's actually like, faster than daily, faster than hourly. If you could think about compounding like every second, faster than that, right? Continuously. There's a different formula. So, first formula, capital A equals capital P times 1 plus R over N, all raised to the NT, like that. Right? So that's for N times per year. And I'll explain what the variables mean in a moment. Continuously is capital A equals P times E to the RT. So you can see now that E is playing a role in this as well. And it really plays a role in a lot of different applications. Finance is just one thing. There's a lot of applications in science with E that you'll study. That there's actually a lot of good problems in our textbook, but we're kind of limited on the time that we have together, so can't do too many of those right now. Now, if you notice here, there's 5 variables. So I'm going to make a chart underneath here, right in the middle, because it really applies to both formulas, what the variables mean. So 5 rows, capital A, capital P, R, N, and T. So capital A stands for the account balance. The account balance after T years. The account balance after T years have elapsed. So that gives away what T is, time in years. Capital P is your principal investment. And I don't know why they chose P. I think capital D would have been better because it's really what your deposit is, what you're opening the account. You go into the bank, you say, here's $2,000. I want to open an account. That would be P. Okay, that's what you're opening the account with. R is your rate of interest. And I'm going to actually highlight this with a different color because you have to use the decimal equivalent of that rate. Okay? If you forget to do that, you're going to get every problem wrong. In other words, if it was 50%, you'd use 0.5. If it was 35%, you'd use 0.35. If it was 10%, you use 0.1. That kind of thing. All right. And then N is not in this formula, so it doesn't apply to this formula. And we already said what it is, right? Number of times compounded per year. I'll just give you a few moments to write any of that. And we're just going to do a problem, all right? And, once you've done 1 or 2 of these, you've done all of them. They're all done the same way. So we'll just do one. We'll call it a day. Okay. Here we go. Suppose you deposit, let's do $8,000. $8,000 in an account paying, let's do 2.25% annual interest compounded blank. Okay. Now they always say, some people say, oh, annually means N is 1. They always say the percent annual interest. You see like APR. You ever see it with like credit cards and that kind of thing? They always classify it as annual interest, and then they tell you how it's going to be compounded afterward. So you got to look after that phrase. All right, and I'm just going to leave that blank for a minute. Find the balance after, let's do 22 years. And find the balance after 22 years. And we're going to do 2 different problems. I'm going to fill in the blank here with, first I'm going to fill it in with the word quarterly. Okay, and we'll do that one. And then we'll do for compounding continuously. So you get a little bit of the, oops, I forgot a letter in there. Continuously. So get a little bit of the flavor of each formula. So I'm going to write down the formula for each one again. So everything in this section of the book, they're asking for just the account balance. So we're going to look for A. As we move throughout the chapter, we might look for P, we might look for time, okay? N is the number of times compounded per year. If it's quarterly, that means N is 4. Okay? N would have to be 4. So we're going to put that in. The principal, 8,000. Interest rate, 2.25%. As a decimal, that's 0.0225. Right? We just said N was 4, and time is 22. 22 years. Now, this is what I need to see from you in terms of work. Okay, from here you can go into the calculator. If you just tell me a number, I'm not going to accept that. So you have to at least give me this first line of work. Right? If you want to write more out, you can. But really, you can do the problem from here now, all in the calculator. You don't want to do it in one step, though. There's a lot of mistakes can be made. So I'm going to tell you how I would do it, and then you can make your own decisions about how you're going to deal with it. I do it in a few different steps. I work from the inside out. So the first thing I would do, grab my calculator, I do 0.0225 divided by 4. I hit enter. And now any kind of scientific or graphing calculator allows you to use your previous answer to continue doing calculations. So I'm going to take whatever that previous answer is, right? So whatever that is, that answer now I'm going to add 1 to it. Right? I'm working inside the parentheses here. And I'm literally writing down nothing in terms of, in my work. This is all I have, just this. So my answer plus 1, hit enter. That gives you something else. That gives you what's the value, basically the total value inside these parentheses. Now you're going to take that answer and raise it to the 4 times 22. I guess you could just write 88 there. Hit enter. And then that whole, right, that's everything to the right over here, times 8,000. So now that answer times 8,000, and then that's it. There should be no rounding, I guess is what I'm telling you, until you get to the end, right? Then we can talk about how it's rounded. But everybody in the room should get the same exact number here. And if you're not, that means you're not doing it the way that I'm asking. So if I do that, again, I've done this beforehand. It comes out to be 13,105.79571. But this is money, okay? Now, you would think that because this is a 5, this would round up to 80 cents. Doesn't. It never does. It doesn't matter if there's a 5 here, a 1 here, a 9 here. The bank never gives you the fraction of the penny. Never. That's how they make the money. It's capitalism. So if you looked at your bank statement after 22 years, that's what it would say. 13,105.79 cents. Right? They always keep the fraction of the penny. The funny thing is, if you had a credit card, right, and your balance to pay them was this number, they always round up the penny. So they always make you pay that fraction of the penny to them. It's kind of messed up, but that's what it is. Now, doing the continuously, it's the same idea. It's actually less steps. You've got the P is 8,000. And then e to the 0.0225 times 22. right? So that's, again, that is the only thing I would need to see from you in terms of the work. And now you can grab your calculator, do E raised to the, again, this is how I would put it in. 0.0225 times 22. I hit enter. And then I do that answer times 8,000. And hit enter. That gives me 13,123.98591. Again, they just truncate the number right here. That's it. That's what your balance is. Okay. And I mean, it's not that much of a difference, right? $20 about. You don't really see difference in finance until you start using large numbers, right? Powers of 10. Right? So if somebody deposited, let's say, $800,000, then the difference is more decimal places down. And that's what, they always say you gotta spend money to make money. And that's what they're talking about. In the large scheme of things, $8,000 is not a lot of money compared to what this country spends on a daily basis. So with this, you will be able to do all the homework. We'll just do some, variety, some more different problems on Thursday, but you can do all the homework now. I'll send out the video in a few hours. Come to conference period if you have any questions. You're free to go. Have a good Tuesday.